All right, so let's look at this one. Polynomials that have this form with a in the real numbers and t's in the real number, and we never get to fix t, but polynomials that look like this. Is this a subspace? Remember, this was the question up at the beginning to find out if this is a subspace. So we already know polynomials are a vector space, but is this set here, is this going to turn out to follow the 3 criteria for subspace? Well, first off, we see there is a 0 vector. If I let a equal 0, we get the 0 vector, right? So I just want to get, so t is never fixed, and you never let t equal 0 to make it do what you want. T is always allowed to go to all independent variables. All right, so that's 1, done, yes, it works. If I take 2 vectors that are in the space, do I stay in the space? If I add them together, I can pull an a plus b out, multiply it times the t squared, so this fits the form that's given. So yes, it satisfies being closed under addition. Take 2 things that are in the space, add them together, I stay in the space. All right, so if I take a polynomial that's in the space and if I multiply it times a real constant c, do I stay in the space? I do. It looks the same, fits the same form. So that is a vector. So this is, so therefore, yes, a subspace. All right, so different kinds of polynomials. So let's go do this one. So polynomials that look like this. So first off, is there a 0 vector? Is what I'm asking myself. Well, I know I can let a equal 0, but does that get me, question, does that get me to p of t equals 0? It does not, right? Because I still have the 1 in front of the t. So there is not a 0 vector. So I could right away say not a subspace. And I could be done. Okay. Or let's go check out another one just for kicks, right? Just to practice, that's all. Just working on the practicing. So let me make it thinner here. Okay. So 2, let's work on the second one. If I take 2 things, so a p of t equaling a plus t squared, and a q of t, another vector, b plus t squared. So those 2 are elements, both elements of the subspace. If I add them together, I get a plus t squared plus b plus t squared, which gives me a plus b plus 2t squared. So the a plus b, that's just a constant, but this 2, so this shows me it is not closed under addition because of this 2 here. It does not fit the same form as what was given. So again, I could be done. I could say not a subspace. Let's just go through the other just so you see. Okay, so if I take an element p of t, a plus t squared that's in there, the question is c times p of t in the space? So if I take c times the polynomial, I get ca plus ct squared. This c, it shows me it is not in the subspace. Doesn't fit the correct form. So the constant, real constant times this does not stay in the subspace. So all 3 of these things fall apart. All right, so is the set just the 0 vector? I don't even need to know what size it is, but the set with just the 0 vector, is that a subspace? Well, first, is there a 0 vector? Got it, done, right? Okay. If I take 2 things that are in the set, well, all I have is the 0 vector, and if I add them together, do I stay in the subspace? Yep. And then if I take constant times the vector, do I stay in the subspace? Sure do. So this is a subspace. I don't even need to know what size the 0 vector is, right? Could be a 3 by 1, could be a 5 by 1, but it is a subspace. All right, so polynomials of a degree at most 3. So you could have a polynomial equaling a polynomial equaling let me make it a naught plus a1t, or a polynomial equaling a naught plus a1t plus a2t squared, right? Up into at most 3, degree 3. Okay, so first off, is there a 0 vector? Yes, right? I can let a naught equal to 0. So I get p of t is equal to the 0, right? With a naught equal to 0, because I'm allowed to fix the a's. So yes, the 0 vector is in there. So 2. Is it closed under addition? So I do have to kind of make up 2 at most degree 3. So a naught plus a1t plus a2t squared plus a3t cubed, and then make a q of t. Let me do b naught plus b1t plus b2t squared plus b3t cubed. Okay, so what I'm trying to look to see is if I add these together, do I stay looking like polynomials of with integers as coefficients, which I haven't brought that up yet because it hasn't mattered. Integers as coefficients, will it stay in the set? So if I join the coefficients, a naught plus b naught plus a1 plus b1t plus a2 plus b2t squared plus a3 plus b3 t cubed. So since these are already integers, I add integers, they stay integers. So that means this is closed under addition. All right, so the third criteria is seeing if I take a constant, a real number c, and if I multiply it times one of the polynomials in here, do I stay in the set that has polynomials of a degree at most 3 with integers as coefficients? Well, if I take c times an a naught, where c is a real number, and then a naught is an integer, they are no longer integer coefficients. Because every time I multiply the c times a real c, a real number, times a naught or a1 or a2 or a3 as integers, they don't stay integers. So no, not a subspace. So this is the only one that doesn't work in this case.